distance. The battle cry of a generation. This life is a precious gift, so don't get too crazy. It's not worth the risk. You know that we are still young, so don't be dumb. Don't trust.
Hello folks. In today's video on lesson 2.6 we're going to be talking about equations of planes in 3 dimensions. So far in this unit we've done many things, but most recently we've been looking at how to represent a line in 2 dimensions using some different equations. In class on Monday I'll show you how we can extend that idea of a line in 2 dimensions up to 3 dimensions. But to get into this video, let's just look at some definitions and some different shapes. A plane, as I've defined before, is a flat 2-dimensional surface that extends forever in 2 directions. So if you imagine a flat desk, and the surface of the desk just keeps going and going and going forever in 2 directions. That's a plane. Looking at different dimensions, we have 0 dimensions. The shape we're looking at is a point. 1-dimensional shapes are a line. It has a length but no width. 2-dimensional surfaces have a length and a width. 3-dimensional surfaces, like a cube, length, width, and depth. And then if we want to get creative, 4-dimensional surface is called, or one 4-dimensional surface could be called a hypercube. That's a cube inside of a cube. But today we want to talk about planes. For an equation of a plane that's represented as a vector, we need 2 things. We need a point on the plane, and we also need 2 vectors. That are on the plane. So just to show this as a diagram, if I have my x, y, and z axes to describe an equation of a plane in 3 dimensions, I need some point. We'll call that point P naught. I need 2 vectors that are sitting on the plane. Let's call that the vector B and the vector A. And if I can find those 3 things, then I can create an equation that describes the plane. And the equation for a plane, a vector equation for a plane would be r equals, we'll call this r1, some point on the plane, plus some scalar multiple of vector A, plus a scalar multiple of that vector B. So again, we have a point, we have the 2 vectors that are on the plane, and we have our parameters s and t that are real numbers. So as an example, we can find the vector equation of the plane containing points P, Q, and R. And once we've found that equation, we can find out if point T lies on the plane. So, remember, I need a point, and I need vectors, I have a point. I can use the point P. And with these other 2 points, point Q and point R, I can create vectors with point P. So I can find the vector PQ, and I can find the vector PR, and I can use those vectors as my vectors that are on the plane. So vector PQ would be head minus tail, point Q minus point P, or the point 2, negative 3, and 1 minus the point 1, 0, and negative 3. So vector PQ will be the vector 1, negative 3, and 4. PR, again, will be the head, R, minus the tail, P. So vector 3, 5, and negative 3, minus point P, 1, 0, and negative 3. Or the vector 2, 5, and 0. So my plane, as we said, is equal to some point on the plane plus a parameter S times the vector A that's on the plane plus a parameter T times the vector B that's on the plane. So filling in what I identified my point as, which was 1, 0, and negative 3, plus S times my first vector, 1, negative 3, and 4, plus T times my second vector, 2, 5, and 0. So this is my equation, my vector equation of my plane. This is the vector equation of a plane. The past few days we've been looking at vector equations of lines, and we noticed that we could separate the vector equation of a line into something called parametric equations. We can do the same thing for a plane. We can create parametric equations based on x, y, and z components. So the x component of this plane would be 1 plus s plus 2t. The y component would be 0 minus 3s plus 5t. And the z component would be negative 3 plus 4s. So to answer the question, does t, the point 5, 7, and 1 lie on the plane? Well, I can take each of these parametric equations and I can see if there's values for s and t that I can plug in for the parameters that would make the x component equal 5, would make the y component equal 7, and would make the z component equal 1. So I have 3 equations. And 2 unknowns. I can try and solve these equations to see if there are indeed values for s and t that make this true. So by bringing the negative 3 over to the other side in equation 3, I get 4 equals 4s, or s equals 1. I can take this value and plug it into the s value in equation 2. So I get 7 equals negative 3 times 1 plus 5t. Solving for t, I get 10 equals 5t. Now that I know my values for s and t, I can go to equation 1 and plug them in for s and t in equation 1. So 5 equals 1 plus plus 1 plus 2 times 2. So on the left-hand side I end up with 5. On the right-hand side, 1 plus 1 is 2, plus 4, I get 6. So I get the equality 5 equals 6. We know this isn't true. There's no more variables here, there's nothing I can manipulate. When we see a statement like this in mathematics, 5 equals 6, or a number equals a different number, that's math's way of telling us that something's not working. And what's not working is this point T is not on the plane we've described. So we've defined the vector equation of a plane, we've defined the parametric equations of a plane. And we can now define the Cartesian equation of a plane. For the Cartesian equation, we need a point, and we need a vector that is perpendicular to the plane. We need a vector that's a normal to the plane. We need to find a normal vector. The equation, the Cartesian equation of a plane, is of the form ax plus by plus cz plus d equals 0. It's similar to the Cartesian equation of a line. And because it's similar, we can extrapolate that the normal vector is equal to the coefficients a, b, and c. So using the same coordinates as our first example, let's find the Cartesian equation of the plane containing these 3 points. So from the work we've already done, we know that the vector PQ, the vector that lies on the plane, is the vector 1, negative 3, and 4. We know the vector PR is equal to 2, 5, and 0. We can use these vectors to find the Cartesian equation because we need a normal vector perpendicular to the plane. If these two vectors are on the plane, we need to find PQ crossed with PR to get that normal vector. PQ crossed with PR will equal the normal vector. So using the algorithm for cross product, cross out the first and last column. So my perpendicular vector will be the vector 0 minus 20, 8 minus 0, and 5 minus negative 6, or the perpendicular vector negative 20, 8, and 11. And based on our definition of what the normal is, these are my A, B, and C components of the Cartesian equation. So I have negative 20x plus 8y plus 11z plus an unknown d value equals 0. I can use point P to find my unknown value d. Because the point P is on the plane, I can sub this in for x, y, and z. To solve for d. So I get negative 20 plus 33 made a mistake. It should be a negative 3 that I'm subbing in for the z value. So negative 20 minus 33 plus d equals 0. Bringing the constants to the other side, I get a d value of 53. So now I can say that my Cartesian equation is negative 20x plus 8y plus 11z plus 53 equals 0. However, we need to follow proper form for Cartesian equations, and proper form tells us that the a value has to be positive. So I'm going to multiply through by negative 1. So my actual answer is positive 20x minus 8y minus 11z minus 53 equals 0. So really, we've seen three different ways to represent a plane today: the vector equation, the parametric equation, and the Cartesian equation. I'd like to talk a little bit about what you can expect on your unit test. On your unit test, you need to make sure that for knowledge questions you can perform the dot product, the scalar and vector projections, and the cross product. You want to make sure that you can determine the vector, parametric, and Cartesian equations of a line, and the vector and Cartesian equations of a plane. For application, you need to be able to use any of the above properties in the knowledge category to prove a property, to find the area of a parallelogram, to determine torque and work, to determine if vectors are really perpendicular, to find angles between vectors, to find an angle the vector makes with the origin, that's direction cosines, and to determine if a point that I give you is on a line or a plane. For thinking questions, you need to ask yourself, can you take what you've learned and extend it? Can you work backwards in a formula? Do you understand the concepts that we've covered in class fully? Have you tried your homework questions twice, and have you looked at the questions indicated as thinking questions in the textbook and tried some of those? And then lastly, for communication, can you talk out loud about what you've learned and about what it means? If I showed you the solutions to a question, could you explain the steps that you've done in order to get that solution? If you can do all those things, you're going to be able to do really well on this test. That will be on Thursday of this week. This has been a long unit. Having the test on Thursday means that we're going to get 2 full days of review on Tuesday and Wednesday. If you want to start working early, you can. The homework that I'm going to assign, at least part of it for today's lesson, are some questions on page 459 and 468. And if you want to get started on the unit test review, you can take a look at those questions on 418 and 480 and start to try those. Otherwise, I hope you have a good weekend, and I'll see you in class on Monday.